Hello and welcome back to Calculus 3, section 15.7 on minimum and maximum problems. So this is known as optimization in Calculus 1, where the goal was to find a point where the function has a minimum or it has a maximum. So if we travel back in time to, again, Calc 1, we remember that in order for us to do these problems, we set the derivative equal to 0 to find the point. So let's say you have a river and you have some kind of a rectangular plot with dimensions x and y, and you want the max area given 2,000 yard of fence. So what are the dimensions so that area is maximum? Well, your objective equation is going to be xy is a max, because you are trying to, that's the object, right, of the problem. You are trying to figure out the maximum area, and the constraint is that x plus 2y must be 2,000, because that's how much fence you have, which is the black line going around. So this is a standard Calculus 1 problem, and you solve constraint for x, which is 2,000 minus 2y, and then you plug that in the objective equation. There we go. I was missing a b. And now you say 2,000y minus 2y squared equals a max. Max is some area we don't know. It's also a variable. And this is where you hit this with the derivative. Now, since we are working in respect to y, we'll do the y. And we have 2,000 minus 4y equals 0. So this is that part where we said you set your derivative to 0, but it's not, you're not setting it to 0. It's actually the derivative of whatever number this is. This is going to be eventually some number in thousands of yards squared. So I don't know if that's 100,000, if it's 1,000 yards squared, it's something, right? But I know it's a number. So the derivative of that is 0. So you're not setting the derivative to 0. It's just derivative is equal to 0 because it's a problem on, it's a problem on optimization. So now y is equal to 500 yard. When you solve this equation, right, 4y equals 2,000. 2,000 divided by 4 is 500. And that will give us that x is equal to 1,000 yard. And now we know that the dimensions are 1,000 by 500 yards. And that will yield maximum area. So this is a standard Calculus 1 problem. Most of you should have this on your exams, either the exam or the final, which outlines this procedure. Now, once we have the knowledge of what's happening in Calc 1, now we're switching to Calc 3, and we are going to do the same calculation, except this time our critical points will be given by partial derivatives. So partial derivatives are the ones that will drive everything. So For Calc3, we start with the critical point. We calculated our critical point earlier was y equals 500. That was a critical point. So, critical point, we'll say n interior point AB in the domain of F is a critical point if either, and now, number one, partial derivative in respect to x equals the partial derivative in respect to y equals 0, or at least one of partial derivatives does not exist at AB. At least one of partial derivatives does not exist at AB. So this is a standard critical point. Now we just adopted this for Calculus 3 3D. The procedure is going, as you can see, is the same. Find the derivative, set it equal to 0. Now find two partial derivatives, set them equal to 0. Now that creates problems. Because earlier you had an equation and you just solved that equation. Remember what I did? I had an equation and I solved that equation and I get y equals 500 and woohoo, right? Done. Now you have system of equations, because look, fx is going to give you an equation, fy is going to give you an equation, so you have two equations, so you have multiple points that satisfy that, possibly. In addition, there are just systems of equations. They could be systems of nonlinear equations, which actually don't have rules for solving. So you just have to play with them until you get the problem, get the solutions. So let's take a look at some examples. And see how this is done. Should we get the example for this or do the secondary? Let's do the whole thing first and then we'll do the examples. So once you find critical points can be one of the three things: minimum, maximum, and the new point called the saddle point. So you guys now have three possibilities when you get the critical point. They can be either min, or a max, or a saddle. Now, to determine which one it is, we use the second derivative test. Second derivative test says, suppose the second partial derivatives of f are continuous throughout an open disk centered at the point AB. Great. Suppose the second partial derivatives of f are continuous at AB, where fx AB equals fy AB equals 0. So this is just telling you that AB is a critical point. And here's the equation that you must know: d of xy be the partial derivative, second partial derivative of xx times the second partial derivative yy minus the mixed derivative xy squared. So this is the equation that for the second derivative test that you are using to make these, to sort the points. So now let's take a look at the cases. So number one. Oh, come on. I ran out of ink. There's no more ink in my pen. You can see I'm trying to write, but there's just no more ink. I guess I'll have to use the sharper. Oh yeah, to draw blood. Oh, why? I need to write 4 lines. Now I gotta make a separate video, part 2, midway through the theorem. I don't even, is the stream still going?
Still on.
Can I restart the? No, the screen is not working. That's the annoying part. Let's see. Yeah. Oh, come on. Let's see if this helps. All right, good. So 4 cases. Number 1. If d at AB, which is the formula you're calculating up there, is larger than 0, and fxx at AB is smaller than 0, we have a max. Number 2, if dAB is larger than 0, fxx AB larger than 0, we have a min. Number 3, if dAB is less than 0, then we have saddle. And number 4, if dAB equals to 0, test is inconclusive and you should cry. So we need this. The formula for D, that's the second derivative test. And then if you remember your Calculus 1, the second derivative test was connected to concavity. So when stuff is concave down, that means it opens downwards. It has a maximum. So the second derivative being less than 0 meant concave down and it had the max. Look, concave down and it has a max. So everything is fine. When something is concave up, it has a minimum. Well, concave up has a minimum, right? So all of the things that you learned in Calculus 1 are still the same. The only thing that it's new now is you have this annoying formula here, and it's just really good luck with calculations, because the problems here, the systems that we have to solve, sometimes tend to be really annoying. Let's take a look at some examples from homework, and then we are going to do the second part of this lecture, where we also have to check the boundary. So this is, if you think about the planet Earth being a ball, right, sphere, and there is terrain on top of it everywhere, and there are little hills and valleys and so on. So there are a lot of local maximum points, local minimum points. There are a lot of saddle points, right? If you have two hills adjacent, right, that are going into a valley like this, but then at the valley where the stuff goes up, you also have going down, there will be a saddle point there. So there's a lot of these types of points, let's say, on the surface of the planet. So if that is so, you don't have a bounded region to work on, but then you look at the surface of this desk and it ends, right? So we would have to check separately for the boundary. Now obviously I'm going to draw the parallel to Calc 1 again when we get there. So let's take a look at analyzing critical points using second derivative test. The first problem is going to be vanilla problem. So let's go with 24. F of x, y is given as x to the 4 plus y to the 4. I'm going to regret this because the derivatives will have cubes. And minus 4x minus 32y plus 10. That's the function. So this is all you're given. That's it. Now you are supposed to find min, max, saddle. That's what you're supposed to find, min, max, or saddle. So you start by getting all 5 derivatives first. Because when you have all of those 5 derivatives done and on a pile, you can just refer to each one of them, rather than stopping your calculations to then get another derivative or something. So let's just get fx really quick, which is 4x cubed minus 4, and then get fxx immediately next to it, which is 12x squared. Then we get fy, which is 4y cubed minus 32, and get fyy immediately, which is 12y squared. And now we also need fxy, which is the same as fyx. It doesn't matter which one you compute, so you can take a look at the top, take the derivative in respect to y, you get 0. You go on the bottom, take the derivative in respect to x, you get 0. So it doesn't matter which way you look at it. The fx derivative would be 0. Great. Now, the annoying part. Set fx equal to 0, which is your 4x cubed minus 4 equal to 0, and set fy equal to 0, which is 4y cubed minus 32 equal to 0. And your job is to solve. Whatever method works. Sometimes you have linear equations, sometimes you have these nonlinear. These are nonlinear equations. Now the good thing is that these equations are not coupled which means that one will have its own set, the other one will have its own set of solutions, and you just combine the points you get. All right, so from the first set, you have that x cubed is equal to 1, from where x is equal to 1. Awesome. From the second set, you have that the y cubed is equal to 8, from where y is equal to 2. So we just got that our point AB is 1, 2. So you cannot get a simpler problem than this. Zero effort. So now that we know we know our critical point, we need to learn, right, to investigate if it's min, max, or saddle. And we'll achieve that by computing D at 1, 2. Now D, that is going to be fxx, fyy minus fxy, and all of that computed at 1, 2. So fxx is 12x squared, times 12y squared, because the fyy is 12y squared, minus 0 squared. So D at 1, 2, so D is larger than 0. Now if you go over here and you take a look at D larger than 0, then the point that we are looking at is either a max or a min, depending on, because we got D larger than 0. That's first two cases. So now your fxx is either larger or smaller than 0. So fxx is 12. fxx is 12. So fxx is larger than 0. When you have both of them larger than 0, we have a minimum because it's concave up, and being concave up, it has a minimum. So 1, 2, and f of 1, 2, right, if you are computing the z value, is a minimum.
So that you know, at school, Wi-Fi is all weird and messed up, so your screen is like, it's just
In and out, yeah.
not even, like it just goes like 3 seconds and then it buffers and then skips.
Well, we'll see, maybe we'll see what happens. So you can always look at the older lectures when.
I do myself on relax.
Terrible. Let's try problem 30. F of xy is equal to x to the 4th y squared. Again, looking for min, max, saddle. Min, max, or saddle. So what is happening here? Well, we have our 5 derivatives to find. The derivative of fx is 4x cubed y squared. Derivative of fxx is 12x squared y squared. Partial derivative in respect to y is 2x to the 4y, and fyy is going to be 2x to the 4. Now, to find our mixed partial derivative, we can do either xy or yx. Now it's easier if you do yx because it's already 2x to the 4th. So it's going to be, No, we have to look here. What is my partial derivative? I have in respect to this one in respect to x. So it's going to be 8x cubed y. Okay, let's check now this one in respect to y, 8x cubed y. Good. So either way, they're good. Perfect. So we have our 5 derivatives. We have first derivatives here and the second derivatives on a pile for d there. Now we have to solve 4x cubed y squared equals 0 and 2x to the 4th y equal to 0. Now the only point that fits this is going to be 0, 0. No other point would fit as a critical, right? So now, what do? Well, we compute our d, but the d at 0, 0 is just going to be also 0. So test is inconclusive. You have to have larger than 0 on d to get either min or max, less than 0 on d to have a saddle point, and then you also have to, and if you have equal to 0, test is inconclusive. Now, if the test is inconclusive, does that mean we are done with the problem? No, right? Because we would still like to know what's happening at 0, 0. Is it a min? Is it a max? Is it a saddle point? So what you do is you can calculate at the points around it and see what is happening with the z value. Now this is again painful, right? Because you're doing a lot of tedious calculations. But the idea is now to check 0.10, 0, 0.1, and negative 0.1, 0, and 0, negative 0.1. So what I did here, if you look at the calculation like here, if this is, let's say, 0.1 on x-axis, negative 0.1 on x-axis, positive 0.1 on y-axis, and negative 0.1 on y-axis. So what I'm doing is I'm computing 4 points around this and looking at their z values. If the z values are above, right, then the point is a minimum. If the z values are below, the point is a maximum. If some are up and some are down, it's a saddle. See, when I'm computing z values, if I have a maximum point, then all other points, see, if my maximum point is at 0, 0, then if I calculate 0.1, negative 0.1 on any of the values around, they will all have a smaller z value than the one on the top. As I said, it tends to be really annoying and long and painful, but you know, such is life. Let's take a look at 36. It looks terrible. X minus 1 divided by x squared plus y squared. We immediately know that the derivative does not exist at 0, 0. But neither of the derivatives exist at 0, 0. And 0, 0 is not min and not max. And we also have to kick it off the list, because if you have 0, 0 as a point, there is no function value there because the derivative is equal, the denominator is equal to 0. So 0, 0, no min, max. So that's where we start. Now we need derivatives. So the first derivative is fx. So that's going to be a quotient rule. X squared plus y squared, everything squared. X squared plus y squared times 1 minus x minus 1 times 2x. So we have x squared plus y minus 2x squared plus 2x divided by x squared plus y squared squared equal to 0, right? So y squared minus 2, no, y squared minus x squared, because one of these cancels, plus 2x over. Now, good thing is we don't have to worry about denominator, because when we set this equal to 0, denominator just goes away when you cross multiply. So that part is at least easier. Now, partial derivative in respect to y. Well, we don't have to worry about partial derivative in respect to y that much, because it's not a quotient rule. You only have a y in denominator. So you can regard the problem as x minus 1 times x squared plus y squared to the negative 1. So we're going to have 1 minus x, because the negative would flip. And then have x squared plus y squared to the negative 2 times 2y as a chain rule. Take derivative any way you know from Calculus 1. And then simplify this into 2y 1 minus x divided by x squared plus y squared, everything squared. And now we get to set each one of these to 0. Oh, I need second derivatives for each one. Kill me now. fxx. So this is going to be yet another quotient rule. This one is going to be a little bit spicier. X squared plus y squared, everything to the 4th power now. We have x squared plus y squared, everything squared. Let's copy the denominator. Derivative on the top in respect to x is going to be negative 2x plus 2 minus copy the top, y squared minus x squared plus 2x times the derivative of the denominator. 2x squared plus y squared to the 1st power times the derivative of 2x as a chain rule. Hey, look at that. This is called mathematical gymnastics. You go and you flip and so the first parenthesis, the parenthesis here can be simplified. If you kick out negative 2, you are left with x minus 1. Then you square this one, which is x to the 4th, plus 2x squared y squared, plus y to the 4th. Great. Minus I said I'm gonna regret this. Plus 2x, and then we have 4x cubed plus 4xy squared divided by, we don't care, denominators go to 0 anyway. Oh no, they won't in this case. Great. fxx Keep going. So now I have to FOIL both of these. They're going to have 1 million terms. It will be better if I just left this as 2 minus 2x, because now I got to FOIL. 2 times everything, that's 2x to the 4th plus 4x squared y squared plus 2y to the 4th minus 2x to the 5 minus 4x cubed y squared minus 2xy to the 4th. So that's the first one. Minus, now we have the second one. That's going to have another 6 terms. So maybe go to the next line. So this is still the same. You know what? I'm going to put the minus here. So what do we have? We have y squared times each one. So 4x cubed y squared plus minus, because of the minus in front, 4xy to the 4th. Minus and minus gives me plus 4x cubed. No, 4x to the 5th. 4x to the 5th. And then plus 4x cubed y squared. And with the 2x, and we're done. So minus 8x to the 4th. Still doesn't fit. One more term. Minus 8x squared y squared. Great. Like terms. Oh, by the way, we need to do this for fyy and fxy. And then we need to compute that in whatever we get of the points. Did I promise that it's going to be terrible?
I think I see a problem number 10 for the next step.
Problem number 10. If you wish. X squared minus y squared to the 4th power. That's the denominator, right? Alright, so now let's see if we have any like terms. And we do. Orange over here. Negative 6x to the 4th. I think I had 5. Yeah, there it is. This one. And this one. So plus 2x to the 5. And now I have, well, they pretty much all pair up. I have this one and this one. Minus 6xy to the 4th. Two y to the 4th doesn't have anything going with it, so we'll just leave that one there. What else do we have? X squared y squared. X squared y squared. There it is. So minus 4x squared y squared. X cubed y squared, they cancel. These two terms, they cancel. And the only thing that is left is this single negative 4 cubed. Now I wonder if I by accident doubled up on this term. 1, 2, 3, 1, 2, 3, 4, 5, 6. X cubed. Now we're all good. So this one is done, this one is done, this one is done, that's done, that's done. Minus 4x cubed y squared. That's it. Woohoo!
Where did we get x squared minus y squared?
Is it minus or plus? It's plus. Where do we get it? Nowhere. Thank you. All right, good. fxx is done. fyy. fyy. All right, well, that looks better. What about 7 seconds? So we have our x squared plus y squared to the 4th, x squared plus y squared times the derivative of top, which is just 2 1 minus x, and then minus the derivative on top in respect to y is, no, copy the top, 2y 1 minus x, and derivative of the bottom, 2x squared plus y squared times 2y. Excellent. So now we just need to simplify this. So fyy this is going to be 2 minus 2x, so it's easier. Well, then you won't know where it came from. So let's just go x squared plus, no, x to the 4th, 2x squared y squared plus y to the 4th times 2 minus 2x. And now multiply here as much as you can. Minus, we have, well, multiply 4y, so I'm multiplying these together and these together. So 4y minus 4xy times, now in the second circle without including the 2, we have 2x squared y plus 2y cubed divided by x squared plus y squared to the 4th. fyy is not a problem at all, as you can see. Two x to the 4th plus 4x squared y squared plus 2y to the 4th minus 2x to the 5 minus 4x cubed y squared, that's a 4, and minus 2x y to the 4th. So that's the first part. And now we have minus the second part, 8x squared y squared, and then minus 8y to the 4th, and then plus 8x cubed y squared, and finally the last one, positive 8xy to the 4th. And this is x squared plus y squared to the 4th. So this just carries here, and now we can simplify it and be done. Next time someone tells you that algebra problems are long, because they had 6 steps. There's only 1 2x to the 5, so let's bring that one. 2x to the 4th Square and square. There are no others. No. So that's minus 4 x squared y squared. So we're done with that one. We're done with that one. A cube and a square. These two. That's plus 4x cubed y squared. Oh, look at the last two. Plus 6xy to the fourth. And minus 6y to the fourth. Yes. Good. So I should, I guess, box these so we can find them easily. You know, watch the test being conclusive at the end. Wouldn't that be funny? Alright, we just have fx, y, and then we can go and do the calculations. So what's easier? To go to fx and take the derivative in respect to y, or to go to fy and take the derivative in respect to x? Let's go yx. Let's go with this one. So take the derivative in respect to x. I just copied it here so I can see it. So I need to take the derivative in respect to x because you can work out in either one of these two. So as I'm taking the derivative in respect to x, it's a quotient rule. X squared plus y squared everything to the fourth power. X squared plus y squared everything squared times the derivative of the top in respect to x. Well, that's going to be when you expand this, you get 2y minus 2xy. So in respect to x, the derivative is just negative 2y. No. Negative. When you expand this, you get 2y minus 2xy. You're taking the derivative with respect to x, that goes away. The x will go away, you have negative 2y. I had it right. Minus the derivative of the denominator, which was x squared plus y squared. Now it's going to be a 2 in there. And then the derivative of the inside in respect to x is 2x. So that's the derivative of the bottom, and copy the top, which is 2y, 1 minus x. Excellent. Simplify and we can do the problem. So fxy is going to be x squared plus 2x squared y squared plus y squared, all of that times negative 2y. Over here, I'm going to, let's say, multiply this and then multiply that. So minus 4x cubed minus 2xy squared plus 2 x times this times that. Now, not 2, 4. 4xy squared. And it's 4xy squared. And when you multiply the other one, it's 2y minus 2xy. Just a lot of calculations. So now negative 2x squared y minus 4x squared y cubed minus 2y cubed oh, these are wrong. There should be 4s. See there something is off. 2x squared is to the 4th. Alright, so now much better. So that's not x squared, that's x to the 4th when you multiply there. Then when you multiply here it's correct. And now this is a 5th power here. There we go. Minus, and now I have to FOIL this stuff. 8x cubed y, negative 8x cubed y, and then minus 8x y cubed, minus and minus gives me plus 8x to the 4th y, and the last term, negative times negative is positive, plus 8x squared y cubed. Holy nightmare. The denominator is still the same, x squared plus y squared to the 4th, x squared plus y squared to the 4th. So to simplify this, we look for the same terms in terms of variable. So x squared and then cube, we have that. X to the 4th y, we have that. X y cubed, we have x squared y cubed. Is this x squared? Third term. No. Okay, so let's go. Orange pair, we are looking for, let's say, this term together with x squared y cubed. That's the last term. So I have 8 minus 4, 4x squared y cubed. Minus 2y to the 5, it does not have a match. X to the 4th y, x to the 4th y, so plus 6x to the 4th y. So that's the blue. Xy cubed, I have to copy xy cubed. Well, the rest are all copies. Minus 2y minus 8x cubed y minus 8xy cubed. There it is. So that's the important equation for us because we use this in D. That's important. Great. All right, so now that we have these derivatives done, so fx equal to 0 and fy equal to 0. Now we don't have to copy denominators, just the numerator, because the denominator will cancel when it multiplies into 0. Y squared minus x squared. So y squared minus x squared, should have copied it. Plus, you know what, copy it. That's the derivative, and we set that derivative equal to 0. From where we have equation y squared minus x squared plus 2x equals 0. So that's one of the equations we have to solve. Now fy, go up, look for fy. There it is. This thing, copy, fy equal to 0, and paste it right there. All right, so now set equal to 0, denominator dies. We have 2y, 1 minus x equal to 0. Guys, you have a system of equations. Your unknown variables are x and a y, which would be eventually your a bit for critical point. And you have a nonlinear system, right? These are not linear terms, so that's a nonlinear system. We are just lucky that this equation is so cheap. You use the zero product rule from algebra. So I have y squared minus x squared plus 2x equals 0, and 2y 1 minus x equals 0. These are the two equations that I need to solve. It's like a system, but it's a nonlinear system. Now luckily, from the bottom equation I have 2y equal to 0 or 1 minus x equal to 0. This one solves as y equal to 0, and the other one solves as x equals to 1. Now, if you think you had headaches so far with calculations, let me make clear that point 1, 0 is not what you're looking for, because it doesn't work in the upper equation. If y is equal to 0, then you get 2 minus 1, and that's not 0. So what you got from this equation are two decoupled coordinates, and now you have to plug each one in that equation to find its other value. So when y is equal to 0, we have 0 squared minus x squared plus 2x equal to 0, from where minus x squared plus 2x equal to 0. You factor out x, you get 2 minus x. You get x equals 0 and x equals to 2. So we have a point 0, 0 and a point 2, 0. Now, if any one of these 2 points doesn't work in a second equation, you have to kill it, because it has to work in the other equation. So we use the first equation to come up with these decoupled x and a y. We know they're not a pair for critical points because they don't work in this equation here. So we use them. Here is the calculation for x equals to 1. That's y squared minus 1 squared plus 2 times 1 equal to 0. Y squared minus 1 plus 2 equal to 0. Y squared equals to negative 1. And if y squared equals to negative 1, there's no solution. So x equals 1 doesn't give us a solution. Great. I'm about to cry because none of these work. There's probably a mistake somewhere. I don't know where. Not the derivatives. Don't worry about derivatives. This is just this calculation. Because look what's happening. We calculated our points. I calculated for y these two, and neither of the two work in this equation here. In this equation here. Because 2y equals to 0, y is equal to 0, 1 minus x equals to x equals to 1. So we have this point. And now, if you use y equal to 0, that kills that. You have negative x squared plus 2x. Factor out x. You get 2 minus x. X is 0, x is 2. when x is 0 and y is 0, so 0, 0, plug that in here, we get 2 times 0. Oh no, 0, 0 works. Holy nightmare. 0, 0 works. Alright, so these two work. My brain is dead by calculating all of this. So both of these points work. The other side gave us no solution. Okay, good. Whew. So now our job is to calculate all of that mess up there. Now, to calculate d. Now, please observe that fxx, fyy, and fxy all have x's and y's in the numerator, right? And they all have x squared plus y squared in the denominator. This means that 0, 0 doesn't work, because 0 plugged in for every x and every y will just make everything to be 0 divided by 0. So for 0, 0 test is inconclusive. Because d is equal to 0. The only one that we get to check is 2, 0. Now, before you lose your cool, realize that y is equal to 0. So you are actually crossing out all the terms that have y in it. So you only focus on the terms that have x alone. X to the 3 or 5 or whatever exponent. So my d for 2, 0 is going to be fxx fyy minus fxy squared. And I only get to keep the terms that have x's in them, because y equaling 0 will immediately kill that term. So fxx, let's go. fxx, what do we have? We have these two terms. They survive. And x to the 8 survives on the bottom. Everything else is 0. So negative 6, well, actually I should have copied it. Negative 6x to the 4, 2x to the 5. Divided by x squared squared. This is the term that survived. These are the only ones that survive, and then each x becomes a 2. fyy, the same story. You still have x squared. No, it's squared to the 4th, not square squared. To the 4th, there we go. Now, minus, and you still have x squared to the 4th for xyy. fxy. yy, minus 2x to the 5 plus minus 2x to the 5 plus 2x to the 4th, I believe. I'm gonna verify that. Plus 2x to the 4th. And everything else is dead. Plus 2x to the 4th, right? Good. And minus, the second one needs to be squared. Minus, the second one is fxy. Do we have anything that is just x alone? No. No terms where x is alone. There is y in every term in the numerator. So this is one big fat 0 here on top. And when you square, the whole term just drops to 0. Well, it just became, oh, this is dxy, sorry. Dx and y is 0, so it killed all the y's. That's much better. So what is d of 2, 0? Well, we just need to worry about this. So we have negative 6 times 2 to the 4th plus 2 times 2 to the 5th. All of that times negative 2 times 2 to the 5th plus 2 times 2 to the 4th. Everything divided by, now 2 squared, that's 4 to the 4 times 4 to the 4. And then we'll just cancel a whole bunch of stuff. We don't have to compute all of these. Now, there are cool ways to compute all of this, so you don't have to multiply everything out. We're just going to use algebra to factor a lot. I can factor from the first. I can factor 2 to the 4th. And what's left is negative 6 plus 4. Because there is, I took out of here, I took 4 2's, so 1 2 stays and 1 in front. All of that times, I can kick out another 2 to the 4th over here. And what's left is negative 4. Oh no, I can kick out 2 to the 5. Sorry. I can kick out 2 to the 5. And it's left with negative 2 plus 1. Divided by 4 to the 4 times 4 to the 4. Less than 0. Saddle. Done. Because what is positive? Larger than 0. No. Positive times a negative times a positive times a negative. So you have negative times negative is positive, and then you have all positives when you multiply. We don't care what that value is. We just need to know whether it's smaller or larger than 0. So we have a positive times a negative times a positive times a negative. Altogether, that's positive divided by a positive number on the bottom. It is all positive. So now that we have this, all I need to do is to check if fxx at 2, 0 is smaller or larger than 0. So with this d larger than 0, the problem is either min or it's a max. It's definitely not a saddle. So now I need fxx at 2, 0. But that's easy because that's just this term here, fxx, and that's negative. Two to the 4th, negative 6 plus 4, divided by 4 to the 4 is a negative. So now I have d larger than 0, fxx smaller than 0, so it's a maximum at 2, 0. Or you go home and you redo the whole problem. You do 5 of these in the homework by next year. So let's take a break. When we come back, the second part of this is to include the boundary as well. Which means we do this procedure to calculate all of the min-max values inside the shape, and then we do a couple of Calculus 1 problems at the edge to make sure that there are min and max values along the edge. So we'll do that after the break.